Now we will move to our third presenter, Marlon.
All right, so hello everyone. My name is Marlon, and my presentation is about statistical inferences on the effects of additives on neutral pH polymer electrolytes. In this presentation, I'll be going over some background information, the methodology behind my analysis, and the results. So to start, I'd like to show you all a Ragone plot, which is a plot of the landscape of energy storage devices. As we can see, electrochemical capacitors are devices with large power density. The components of them includes the electrolyte, current collector, electrode, and the separator. This animation shows what the charging process looks like. The charge and discharge rates are fast and highly reversible, and because of that, electrochemical capacitors have long life cycle too. It's those qualities that makes them applicable for applications like electric vehicles, flexible and wearable electronics, and Internet of Things devices. The problem with them is that they have low energy density due to a narrow voltage window of their electrolyte, meaning there's a limit to how much voltage can be applied to the cell. Now, the energy density is equal to capacitance times voltage squared. And so to increase the energy density, an electrolyte with a wider voltage window should be used. That's why neutral pH polymer electrolytes are used. So the qualities of a neutral pH polymer electrolyte includes having a wide voltage window, high ionic conductivity, good mechanical and dimensional stability, high chemical stability, and good environmental stability. The electrolyte I've been looking at has been sodium sulfate polyacrylamide, where polyacrylamide is the polymer and it acts as the host that gives the electrolyte its solid structure. Sodium sulfate is the ion conductor, which allows for ion movement. Now, the problem with this electrolyte is that it has poor environmental stability at low temperature. Because of that, I'd like to show you their plot of capacitance. As we can see, the capacitance is low below -10 degrees. Similarly, for ionic conductivity, it's low below -5 degrees. For these reasons, my summer research goals have been to analyze the effect of using additives for improving the electrolyte's performance at low temperature, and to see if the additives can maintain the electrolyte's properties above 0 degrees. So to do that, the methodology starts by measuring the capacitance and ionic conductivity of sodium sulfate polyacrylamide. I used cyclic voltammetry, which is a technique that measures current as voltage is applied to the cell. The area above the plot is for charging, and below is for discharging. And for my study, I used the discharging, which I'll be representing with Q. To calculate capacitance, it's equal to Q divided by the voltage. I also used electrochemical impedance spectroscopy, which measures the electrical impedance of the cell. The intercept of this plot provides the internal resistance, and with that, I calculated the ionic conductivity with this equation, where L is the electrolyte thickness and A is the electrode surface area. So after measuring the capacitance and ionic conductivity, the next step was to do the same thing, but with this time having the additives in the electrolyte. But before going over those results, I'd like to explain why we use the additives. So the idea behind using them was to lower the freezing point of the electrolyte. Because of that, the additives that we used are chemical compounds that are found in products like antifreeze, which is a product that lowers the freezing point of water-based liquids. One of the chemical compounds found in antifreeze is ethylene glycol, and the way it works can be understood by looking at its phase diagram with water. The freezing point of water is found at 0 degrees, but as the concentration of ethylene glycol increases, the freezing point decreases until we reach the eutectic point, which is where the mixture freezes altogether. This decrease occurs because of the hydroxyls on ethylene glycol structure, which forms hydrogen bonds. Other additives that I used were glycerol and 1,5-pentanediol, and the same explanation applies for them too. So when looking at their plots of capacitance, we can see how by adding ethylene glycol, there's almost no change to the electrolyte's performance. With glycerol, there's an increase, and with pentane diol, there's a slight decrease, but not by much. For ionic conductivity, we can see how all of the additives don't affect the performance of sodium sulfate polyacrylamide. So for that reason, the takeaway from these figures is that the additives do not hinder the electrolyte's performance above 0 degrees, which is one of our research goals. Now we just need to see how they perform at low temperature. So I plotted the capacitance on a logarithmic scale to clearly see the effect of each additive. As we can see, the additives increase capacitance at -20 degrees, but at -10 degrees and up is where glycerol has the increase only. For ionic conductivity, we can see how ethylene glycol and glycerol cause a decrease, but the additives then end up increasing performance above -10 degrees. So these plots only give us an idea of these additives' effect at low temperature. So to get the entire picture, the next thing I did was use statistical analysis to see the effect of each additive. Specifically, I used a software called Minitab to obtain a main effects plot, which is a plot of the mean response values at each level of a process variable or factor, and it's used to compare the relative strength of the effects of various factors. So the factors I used were temperature and ethylene glycol. And temperature goes from -20 to -10 because that is where capacitance was lowest. For ionic conductivity, it was -20 to -5. Now, ethylene glycol has values -1, which is the electrolyte with no additive, and 1, which is the electrolyte with the additive. Additionally, the slope of the plots show us the effect of each factor. And since both slopes are positive, they both have an increasing effect on capacitance, where temperature has the greatest effect because of its larger slope. So I used the main effects plot for all of the additives, and here's a table of the results. We know that ethylene glycol increases capacitance, and it also increases ionic conductivity. For glycerol, it has an increasing effect on capacitance, but no effect on ionic conductivity due to the horizontal slope. And for 1,5-pentane diol, it has an increasing effect on capacitance, approximately no effect on capacitance, and an increasing effect on ionic conductivity. Minitab also provided quantifiable data, which allowed me to compare the effectiveness of each additive on capacitance, which increases in the following order. I did the same thing for ionic conductivity, but the order is a little different. So some trends can be seen from these results. For example, as the density of hydroxyls increase on the structure, so does the capacitance. But for ionic conductivity, it seems that the hydroxyls can't be too dense nor too far apart for the greatest effect. But more research should be done to understand this best. So in conclusion, the additives indeed improve the low temperature capacitance and ionic conductivity of sodium sulfate polyacrylamide, where glycerol has the greatest effect on improving capacitance and ethylene glycol has the greatest effect on ionic conductivity. Additionally, the additives do not hinder the electrolyte's performance above 0 degrees. Now, future work should be done to understand the effect of additive structure on neutral pH polymer electrolyte performance. So I thank you for listening to my presentation, and I give thanks to the financial support from NSERC, the Department of Materials Science and Engineering, and the members of the Flexible Energy and Electronics Laboratory. So I thank you for listening to my presentation, and I now welcome any questions.
Thank you, Marlon. Now I'd like to ask the judges if you guys have any questions.
Sure, I can ask a question. This is Glenn Hibbard. Nice presentation, Marlon. That was really good.
Thank
Can
you.
you go back a couple of slides? Let's go back to maybe slide 14, where you're talking about and you're trying to bring it back to the molecules themselves. Maybe talk a little bit more here about one molecule versus another versus, I like what you were saying about how the relative effects of the hydroxyl groups not being too close, but so maybe can you comment on that a little bit more, please?
Yeah, sure. So for capacitance, we can see how pentane diol has the least effect on increasing capacitance. And the reason for that is because of how far apart their hydroxyls are, which makes it less polar compared to ethylene glycol and glycerol. Now, between ethylene glycol and glycerol, we can see how the glycerol has more hydroxyls, and the separation for both of them are equal. And for that reason, glycerol is the more polar structure. And so the trend here we can see is how as the density of hydroxyls and the polarity increases, so does the capacitance. And that is where some room for more research appears, because we can see how the structure clearly has an effect on the capacitance. And similarly, for ionic conductivity, the trend is a little different, because we could see how glycerol, glycerol is the most polar structure, but it has the worst effect on ionic conductivity compared to the other two. So that's why more research should be done to understand these effects best. So for this slide, I just wanted to shed light on the fact that the structure influences these effects.
Okay, nice. Thank you. Yeah, that's great.
Any other questions?
Hi, Marlon.
Hi.
I'm Solmaz. Thanks for the
Hey.
presentation. Nice work.
Thank you.
And I have a quick question. If you also had a chance to study the interactions of these additives with your polymer, because of the different numbers and then size difference between your hydroxyls group, there might be some interactions between your additives and your polymer too. So maybe it's not only the additives. Did you also have a chance to look at it?
Unfortunately, I didn't. The only polymer I was able to look at was polyacrylamide, because I used data that was provided to me from my supervisors. So I couldn't go into the lab to try out and look at the data with other polymers.
I see. Okay. Okay. No worries. Okay. Thank you so much. Thank you.
No problem.